Okay, Bismillahirrahmanirrahim. So we continue for this video number 3. I think the last video for this topic, chapter 5, torsion loop. So this is the third video and the last video. Right, so let me share the screen. All right, so this time we stop at here. Example on how we can the torsional load, internal torsional load for each segment, and we use the right hand rule sign conversion to determine the direction, either negative or positive. All right, so for this video we are going to cover example 7. Okay, example 7 here. Okay, let's do it. So the gears attached to the fixed and steel shaft are subject to the torques shown in the figure. If the shear modulus of elasticity is G equal to 80 gigapascal, and the shaft has a diameter of 14 millimeter, determine the angle of twist in total. The shaft turns freely within the bearing at B. So there are many clues here given in the question. The first one is the elastic modulus. Okay, this one. Number 2 is the diameter of shaft. So the shaft having the same diameter. So from AC, okay, CD and also DE, the diameter is similar, which is 14 millimeter. Okay, and then another clue here is the shaft turns freely within the bearing at B. So we have a bearing at B here. Okay, so the clue here, there is no friction at all. So if you consider friction, then the other equation, the other method should be implemented. But in this case, there is no friction. So we can ignore the B shaft, B bearing. Okay. All right. So the thing that you have to find is angle of twist in total. So basically, every single bar or beam from AC, for example, have their own angle of twist. Okay. So they have angle of twist here. AC. This one is CD. This one is DE. Okay, so you have to total everything here. So you have to sum up from A to C, from C to D, and also from D to E. This is the thing that you have to find to solve this question. Okay, so if you keep blurring or confusing or do not know how to do, so I suggest you to write down everything, every single equation that you know. For example, angle twist is equal to TL over JG. Okay, so you can get something from this equation. For example, the length. Okay, the length is given. This is the length. This is the length. This is the length. 0.4, 0.3, 0.5. J. J you have to use formula lah. Of course, given formula of J is equal to pi over 2 C, right, C power of 4. So this is the equation of G. Since the diameter, okay, the diameter is similar, so this is diameter, C should be 7 mm lah. So since the diameter already similar, so it will be constant for every single beams. And J is here, G is given, G is given. So the only thing that you need to find is T, internal torsional load. Okay, so how to find it? Again, you have to draw FBD. So how to draw? This is the solution. Okay, so the first one, you have to cut at in between AC. Second one is in between CD. The third one is between D. Okay, so let me change the color. All right, so you have to cut here. Number one, cut number two, cut number three. Okay, there are three cutting sections that you have to do to get the FPD and to get the internal torsional load. Okay, let's say we start with number one first. So you cut at number one, you will have a two split body again as usual. So the best way is to choose the simplest FBD, which is left part. Okay, as shown in this slide. So we are choosing the left part for this number one here. Okay, number one. So you have external load one only, one external load only, which is 150 Newton meter. And the other one, the cutting part, which is here, okay, this is the cutting section, okay, having internal load of torsional. Okay, so we denote as TAC. So it should be other way around. Okay, action and reaction. Okay. So based on this first FBD, you will get straightforward the value of internal load of torsional. Okay, which is TAC equal to 150 Newton meter. Simple. Okay, so number two, you cut at two, you have left and right. So it's up to you. You want to choose left or right, it's up to you. But in this solution, we choosing the left part. Okay, so left part we have external load of 150, and the other external load is 280 Newton meter. And the internal load of TCD, you cut it here, you cut cutting section. Okay, you cut at the point, so you will have internal load of T, so it should be other way around with the nearest external load. Okay, so external load of 280 is clockwise, for example. The TCD should be anti-clockwise. Okay, so from here, from this FBD number two, you will get TCD, okay, using the equilibrium system. Okay, for example, I make it here, summation of moment equal to 0. Okay, you have to define the moment. Let's say the anti-clockwise is positive, so it should be 150 minus 280 plus TCD equal to 0. So you will have TCD equal to 130. As simple as that. So we have TCD. All right. So that one is number two. Okay, how about number three? You cut in between D and E. All right. So there will be only one solution. I mean, one part that you have to consider. You cannot use right hand side of the FBD because there is no external load. You cannot get anything. So we are taking left part. Okay, so you have 150, 280, and 40 Newton meter for the external loads. And then the internal load is pointing different direction of the 40 Newton meter. You should be here, okay? And then again, using the equilibrium system to find the TDE, which is the internal load, okay? And define anti-clockwise positive. So you will have 150 minus 280 minus 40 plus TDE. It must be equal to 0. So TDE equal to 170 Newton meter. Okay. So very straightforward, very simple, easy, right? Okay, so once you have the internal load of each segment, each FBD, and you have to determine the sign convention first, okay, to be included in your calculation. Okay, so the one is step number 2. So determine the internal torque at each segment. So you have the internal torque of the magnitude, not direction. Okay, because direction in the FBD and direction in the calculation is different. So the step 2 is actually wanted to show you to get the correct sign conversion for the calculation. Okay, using right hand rule for the first FBD, okay. So TSC should be positive. So forefinger again following the TSC direction here, TSC direction. So forefinger is pointing like this one, for example. So and your thumb finger like this one. So if your thumb finger is pointing upward, means that the TSC is positive. So that's why we have positive here. Okay. All right. TCD. TCD is beam. So it should be like this one. Okay. So TCD, you put four fingers following the direction of this TCD. Okay, like this one. Okay. And then, sorry, let me change the color. Okay. This one is okay, forefinger, and then the thumb should be pointing inward like this one. Okay, so if the thumb is pointing inward, means that the TCD is negative. So that's why we get the negative value of 130. And same goes this one. Okay, four fingers following the direction of the TDE. So thumb finger is pointing inward. So you will get negative as well. As simple as that. So sign conversion is important. If you are converting wrongly, you will get wrong answer. Okay, so we have the internal load of T, AC, T, CD, TDE. You back to this one. So once you have T, okay, because this one is not individual, so you have to have a summation. Okay, summation of angle. Okay, T done, L is given J, okay, and G is given J, calculate J. So step 3 is calculating the J value, which is the polar moment of inertia. So the J equation is pi over 2 times with radius power 4. So just put the radius, which is R or C, 7 millimeter. Convert directly into the SI unit 0.0071, yeah, meter. So you convert into the SI unit, you will get the J straightforward. Okay. So T have, J have, G have, L also have. So you can use this formula to get the angle of twist. Okay. So this is the formula, summation of TLG, TL over JG, sorry. So T should be individual, okay, T in the step 2, okay. L also individual, okay, because the beam having different length, okay. We have a 0.4, 0.3, 0.5, okay, so this is the length, okay. So put individual into the equation. JG will be constant. JG, G is JG. JG, JG is same lah, constant lah. In this case. Okay, so substitute everything into the equation using calculator, simplify it, then you will get the final answer of the angle of twist, which is negative 0.212 radian. And make sure you set your calculator in radian mode. Radian mode. Even though we are not using the angle, I mean the angle value, but to be safe, set it your calculator in radian mode. Okay, so you will get the radian in the end of the day. Okay, this is the answer. All right. So example 8, I'm not covering this one. You can do with your friend. You discuss with your friend. Okay. So the answer is given. You can discuss and do it together with your friend. As I mentioned earlier, solid mechanics, static dynamic, it is much more on calculation. So no matter how, you have to understand and also do exercise, many exercise as possible. Similar like mathematics that you learn, okay, with other lecturer. So mathematics also you have to do a lot of exercise. You cannot only remember, you have to do exercise more. Okay, so I will continue with the next subtopic. I think it is the last subtopic for this chapter. Okay, power transmission 5.3, power transmission. Okay, so power is defined as the work performed per unit of time. So it is the definition, the work performed per unit of time. And for a rotating shaft, your torque, the power is given like this formula, P equal to T times with omega, where shaft angular velocity, okay, which is omega equal to d theta over dt. Omega is the rotation, okay. That's all we have, angle and also the t. And the omega should be in a radian per second. The unit for the omega should be radian per second. Radian, always radian. And frequency of the of f, okay, f of a shaft rotation is often reported. So normally in the question, in the book, in the examination, in any other cases, engineering cases and so on, the frequency is already given or already reported. Okay, it will measure the number of cycle per second. So F is defined as the number of cycle per second. How many cycle will be rotate? Okay, like an engine. If you're driving a car, you can see RPM there. So rotation per minute. This one is cycle per minute. Okay. Since one cycle, okay, one complete cycle equal to 2 pi, okay, 360 degree, 2 pi radian. So it can be converted into 2 pi radian equal to omega 2 pi f. Okay. So 2 pi is the total cycle, one cycle, f is the frequency. And the power equation, once we have this equation, the power equation can be denoted as P equal to 2 pi ft. So we just substitute the omega into the formula here. So you will get P equal to 2 pi ft. So in the end of the day, we just use this formula. Okay, we just utilize, we just apply, okay, this formula in our case now. So if you are learning mathematics, you are taking mathematics program or the physics, you have to understand from the beginning how to derive the equation, how to get the equation. For engineer as us, we normally apply the equation. Now we are not physician, we are not mathematician, we are engineers. Okay, so next one, okay, if power transmitted by shaft and its frequency of the rotation is known, okay, so if the power transmitter, and the frequency F of rotation is known, the torque can be calculated. Torque is T lah. Okay, so since the formula is P equal to 2 pi, P equal to 2 pi, Ft. So F non P non, you can get T. As simple as that. Okay, for shell design, the design or geometry parameter is given like this one. Sorry, this one. Okay, this formula is coming from the shear formula. Okay, tau maximum equal to TC over J. Okay, so just rearrange like this one. You will get J over C. Okay, equal to T over tau allowable. Okay, as simple as that. And J, as usual, J having different formula for every different geometry. For example, solid shaft, we have J equal to pi over 2 times with C power 4. But for the tubular shaft, having different one, J equal to pi over 2 in bracket C 2 or power 4 minus C1 power 4. Okay, so this one given in slide number 14. Okay, so we use the same J formula. All right. So this is example in daily activities. In industry normally, they have the power system. They want to generate something. For example, in a plantation, I mean, in industry that making maybe Maggie or anything, food and drinks. So they have to move one things to another, from one place to another place. So they have to use this motor system. So this is an example of the motor system together with the gear, shaft, and so on, bearing, and so on. And this is an example of the application of power transmission in biomedical engineering field. Let's say in the future, if you want to become an engineer in the industry to design prosthetic leg, active, we call it active prosthetic leg. So you have to understand a bit about the power transmission as well, even though it's not mean 100% for the biomedical engineer, but as a program of the biomedical engineering, we need to understand about the power transmission. So the power transmission happen here when we have the motor system like this one. Okay, where's the motor? Can see the motor here. This one. Motor. So you have to understand how you can transmit the power from the motor to the shaft. Okay, to the shaft, for example, rod here, screw, and so on. Okay, to rotate something like uh, this one, bearing, for example. Okay, or gear, for example. Okay, the example. All right, so we move to the example 11. This one is straightforward. Okay, a solid steel shaft aviation in the figure is to be used to transmit 3750 watt. So this is the power. Okay, so normally when I read, I just denote what is that the value means. Okay, P is given from the motor M. So we have motor M to which it is attached. Okay, so attached with AB lah. If the shaft rotates at W, not W, this one is omega. Omega equal to 175 RPM. So this one is omega. Omega, but the unit is RPM. Okay. And it still has a allowable shear stress of tau allowable equal to 100 megapascal. Determine the required diameter of shaft. Okay. The nearest MMR, so this is the clue that you need to understand as well as an engineer. Okay, the first thing is required diameter of shaft. So diameter of shaft is here lah. This is the shaft. Okay, AB is the shaft. So let's say I cut it here. You can see the cross section. So you need to find this R diameter. Diameter is D lah. D. Okay, D. So the question is asking you to find the D of the shaft. Okay, the shaft. So how to find and how to get nearest MM I will be explaining later. So this is the thing that we need to find D. So how to find it? As usual, you have to jot down every single equation that you know. For example, tau equal to TC over J. Okay. P equal to 2 pi FT. So when you jot down the equation, you will get some idea how to solve it. So T is not where is T? T is not given, then you have to find the T. Sorry, let me change the color. Okay, T is unknown. Okay, C is the thing that you need to find. I call it KPI lah. Key Performance Index. So your KPI. J is not given as well. Okay, J is not given as well. Tau is given. This J. So J is related to this equation, pi over 2 C power 4. So C is not given. So J means that we cannot get J. Okay, but the thing that we can use in this information is P and also the omega. So P is related to with this equation. Omega is related to this equation. Okay, So P equal to T omega lah. So omega is given, P is given, the omega is given. So you get T. T can be get it from this formula of P equal to T omega. So how to do? This is only briefing or brainstorming the idea on how to get the value. So once you familiar with the idea, the equation, then you can start with the solution. Okay. So okay, what to do now? We solve the t first. Okay, we find the t value first. So omega is 175 RPM. So this one is not SI unit. Okay, you need to convert into radian per second. Okay, so RPM should be a radian per second. So how to do? So I'll explain it next. So this is the thing that we can use where we convert 175, okay, RPM to radian per second. So minutes is 1 minute equal to 60 seconds. So just put 1 over 60, okay, to eliminate minute here. Okay, so to eliminate revision or rotation, so REV, one complete cycle, okay, is equal to 2 pi. Okay, so just 2 pi over 1 REV, you will eliminate REV. Okay, straightforward. So once you have this value 175 times 2 pi divided by 60 seconds, you will get radian per second. So this is the answer for the omega. Okay, once you have raw omega, you have to substitute into the equation of P equal to T dot omega. So P is given 3750, should be in SI unit, which is the SI unit is Newton meter per second. Okay, then you will get T equal to Newton meter, 204.6 Newton meter. Okay, all right. So you have T. Write down again the equation of the tau to Tc over G. Okay, so the thing that we need to find is C. Okay, the J, you can just substitute the J pi over 2 C power 4, like that. Okay, so tau is given, T is already got, C is the unknown. So C is the thing, KPI lah. So T is calculated. Okay, tau is given 100 megapascal here, 100 megapascal. So at the end of the day, you can get C. Okay, so rearrange the equation to get the equation like this one. Okay, put all the values inside, you will get the C. Okay, as simple as that. All right, so sorry, let me check my laptop. Okay, last one. Since we have the C, okay, C is radius. Back to the question, we want to find the diameter, so you have to time with 2 lah. So you get the diameter. So this is also important to you to remember, because last time when you did test 1, okay, you are not answering the question. The test is requesting you to get, for example, radius, but you give the diameter. The question asking you to find the diameter, but you give the answer in radius. That one is a silly mistake. So in this case, make sure that you remember ways to solve the equation, to solve the solution, the answer, to get the answer according to the question. So the question asking to find the diameter, then you have to time with 2, and you have to find the nearest mm. So when you have to 21.84, okay, the nearest mm can be divided into 22 millimeter and 21 millimeter. Okay, this is the nearest one. But in engineering cases, Okay, if you want to design something, you cannot choose the minimum diameter. So the minimum one is 21. The maximum one, the optimum or maximum one, 22. Okay, so as engineer, you cannot choose the minimum one. You have to choose the nearest maximum one, which is 22 millimeter. So this also happened in the test one. You are wrongly give the answer based on the two option. So as engineer, we have to make sure that the shaft is safe to be used. So we need to find, or we need to choose the maximum or the optimum diameter. So for this case, the optimum diameter is 22. You cannot choose 21. If you choose 21, the system will be fail. Okay, because it is have happen for the allowable. So allowable 100 megapascal is only allowed to have diameter of 21.84. So let's say you choose 21, so means that we are not following the allowable stress. Maybe the stress will be higher and then the system will be failed. Okay, so this is the important thing that you know to know. All right, so example 12, example 13, example 14 is your assignment. So I give some solution. This is something that you need to do to discuss and do exercise to get familiar with the solution and the flow on how to get the answer. 3 question within 1 week from now. Okay, you have to submit it to me through e-learning. I will create e-learning link letter and perform a group of 3 people only, 3 members. Okay, together 3. Then you have to submit only one document. Okay, write your name, your team member name, and then include your solution for each example. So we create e-learning link for the submission. Okay, I think that's all. So what you have learned in this topic. So you learn about the torsional deformation of a circular shaft. You learn about the angle of twist in elastic range, and also the power transmission. Okay, those 3 are very important to you. Even though it's not similar like mechanical engineering student. Okay, mechanical they learn a lot, but for biomedical we learn some of them. Okay, so I think that's all from me. Thank you, and see you in the physical class later. Bye bye.